Now that we've talked about our Memoizer that was implemented with the future task, let's go ahead and see how we can apply this to our PrimeChecker app that we've been talking about. So we've used the PrimeChecker app as our running example as we've been talking through various types of interfaces and mechanisms that are defined by the Java executor framework. And now we're going to go ahead and use this in the context of future task. So this particular example will apply the executor completion service framework, which we talked about before, and our future task-based Memoizer to check if n random numbers are prime. As is always the case with this particular family of examples, it's going to be an embarrassingly parallel, a particular use case of concurrent processing, and all the computations are going to be compute bound, so they're not going to block on I/O. The main activity, because of course this is an Android app that you can take a look at the bottom of the link, will check the prime status of count random numbers via the executor service and a thread pool associated with it, and the prime callable class. And of course, under the hood, we're going to use the executor completion service, but as you can see here, we're going to make ourselves an executor service, which is going to be used to actually do the computation. And just for fun, we're going to use a fixed size thread pool, which is tuned, of course, as always, to the number of processor cores by default. Then we're going to use our Memoizer that's based on the future task in order to be able to optimize the checking of the numbers to see if they're prime or not. Here is the prime callable class. We've seen this before in earlier examples. It's going to implement the callable interface, so it can be a two-way call. It's going to have a PrimeChecker field that's going to be a function, which could be a Memoizer, as we'll see, and it's also going to keep track of the prime candidate, and all that stuff gets stashed away in a field. Here's the call method, because it implements the callable after all, and the call hook method will apply the function and check to see what the value is. And keep in mind that this is going to run in a background thread, and it's going to be using our future task-based Memoizer. So it'll go ahead and apply the function, which is going to be a Memoizer. And if we've already computed that value, we'll just return it because it's going to be stashed away in the Memoizer's concurrent hash map. But if we haven't computed it yet, then we're going to have to go ahead and compute it. And the cool thing about using a function, as I mentioned before, is we can transparently optimize it by using a Memoizer. We return a prime result, which is going to indicate whether the candidate number was in fact prime. And the way that works is it's going to be 0 if it's prime as the smallest factor, otherwise it'll be the smallest factor. Here's the main driver program. This is pretty straightforward. You've seen variants of this before. We create a Memoizer, which is going to use a brute force checker. It'll be easy to change this if we want to make a more efficient checker, but we'll just use the brute force one to chew up CPU time for fun. So if you want to change whether you use the brute force checker versus the efficient checker, you just change the parameter that's passed to the Memoizer. It's as easy as cake, easy as pie. And then we go ahead and generate count random numbers between a range that will allow us to have duplicate values. That's why we do this. And then we take each of those longs and we convert them to prime callables, passing in the Memoizer, as you can see here, as the second parameter. And then we turn around and take that stream of prime callables and we go ahead and submit it to the executor completion service. And note that we don't need to do anything fancy with return values or lists of futures, because that's all handled internally by the executor completion service, which, by the way, uses future task in order to queue up the results in its internal completion queue. Here's kind of the way we do the threading for this. We make ourselves something called a completion runnable, which is going to wait for the results that come back through the executor completion services completion queue. And we then have a thread, and we start the thread that will run that in the background. Here's the completion runnable class, which implements Runnable. As you can see, it just has a loop that iterates through all the results. And we'll go ahead and call take, which could block. That'll get the next result that's come back. We then call get on it, because take gives you back a future. Get will then go ahead and get you back the actual value, which in this case is a prime result. And note that take may block if the compute has not finished for the asynchronous computation, but get will never block, because you don't end up in the completion queue until you're completed. And then at that point, we just do a little bit more code to figure out if we have a prime number and print some diagnostics. Because this is an Android app and we want to make it resilient and robust and efficient if someone rotates the phone, we have to store some retained state, and we stick everything in the retained state that's going to be asynchronous and concurrent. So we have our executor completion service, we have our executor service, we have our completion runnable, we have our thread, we have our memoizer. All those things are going to be retained between rotations. And then we use some clever tricks that were baked into Android to make this all work efficiently. This is not the only way to do this, but for this particular kind of use case, it works very nicely. So that's the end of the overview of applying our particular Memoizer based on FutureTask. And you can see it basically looks very similar to what we looked at earlier. It just, this time it uses a FutureTask implementation of a Memoizer so it can be optimized, and it'll work with earlier versions of Java than Java 8, assuming that we define other things you'd need like the functional interface.